Hello there guys and welcome back to another maths video. In this one we're looking at the distributive law of sets, and so there's two different statements as you can see here, and these are some identities from set theory. They also come up in probability and stuff like that. At the moment I'm doing a probability playlist, and this is something that we have to look at first. So you might be coming from set theory, you might be looking at this in the context of probability. What we're going to do in this video is prove statement number one, okay? The way that you prove statement one and statement two is the same. It's literally almost identical. So if I did both, it'd be a bit boring. So, and also the video would be a bit long. So we're just going to focus on statement number one. First of all, let's just unpack what it's saying because that's quite important. So it just says, I'm looking at statement number one. It just says that if you've got some set A and then some amount of sets B1, maybe B2, B3, B4, and it's just any B with a subscript I, where I, lowercase I, is inside of some set capital I. And that set capital I can actually be any set that you want. It could be finite, it could be countably infinite, or it could be uncountably infinite. So it can be anything. It's very powerful. But if you have this setup, if you do the intersection of A and this union of BI's, it's the same thing as just doing the union of A intersect each BI like that. Okay, that's all it says. So let's do just as a kind of warm up, just to get our brains, making sure we understand what the question is actually saying. This is again for number one. Just to explain this, let's say that we just have two lots of, like, we just have B1, B2, right? So basically A intersect the union of, let's say, just B1 and B2, or let's do three. So B1, B2, B3. So let's go from I equals 1 to 3 of the BI's. Okay. First of all, what does that mean? That just means that we're doing the intersection of A and then B1 union B2 union B3. And this is just literally notation. That's not what we're proving. But what we are proving is that this is the same thing as the union from I equals 1 to 3 of A intersect BI. And that's the same thing. If you just unpack this notation, that's the same thing as A intersect B1 union A intersect B2 union A intersect B3. And that's what it's actually saying. So basically in this video, we're proving that this thing here is the same as this thing here, but it's not just for like 1, 2, 3. It could be for any number of unions. So it's very, 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 very powerful. Very, very powerful. Okay, let's go straight into the proof. So the method for the proof that we're going to do is we're going to show that both of them are subsets of each other. Okay, so I'm going to show that A intersect the union of all of those BI's is a subset of the union of the A intersect BI's like this. So I'm going to show this in a second, and then I'm going to show the same thing but with the subset symbol the other way around. If two sets are subsets of each other, they have to be the same set. Okay, so that's basically the principle that we're going to use. And the way that we're going to do that is we're going to do something called element chasing, which basically just means we're going to assume that there is some element X that is inside of this thing. And we're going to show that if that is true, then it has to be inside of this. That will show that we're a subset. And then we're going to do it the other way around. And we're going to say that if X is in this one, then that means that we're in this one. That's basically the outline of the proof. Let's actually do it. Okay, so case one, we're going to go from left to right, showing that the left is a subset of the right. First thing we're going to do for that, as I said, is we're going to let some element X be an element of the thing on the left. There we go. Now I need to show that that means that X is also inside of the thing on the right. How are we going to do that? Well, if X is in the intersection of A and this big thing of unions, then it means that X has to be in both of those two things individually, right? Because if something's in an intersection, it's in both sets. So X is in A and X is in the union over all of the I's in this set of the BI's. It's in both of them. Okay, well, What does that mean? If x, I mean, okay, if x is in A, you can't really say much, it's just in A. If x is in the union, then does that make sense that this implies that there exists some, maybe we could say j, in the set I, such that x is in B J, like that, right? Because if it's in the union, it's got to be in at least one of those sets. It has to be in at least one of those sets. So let's just say it's in J for sure. It could be in several, but we'll say that it's definitely in J. If that's the case, then what we have is that we have that X is in A and it's in BJ, okay? That implies that X is in the intersection of them. So X is in the intersection of A and BJ. And if X is in the intersection of A and BJ, then it is in this union. So X is in the union of the A's and BJ's, or BI's here, from, in the set of I's, okay? Hopefully that makes sense, because again, you would then, hopefully it makes sense. If if X is in one of those BJ's, then that means it's in the union of the intersections of A and BI, because we already know X is in A as well. Hopefully that kind of makes sense. And that concludes that if X is in this left-hand side set, it's also in this right-hand side set, proving that the left-hand side is a subset of the right-hand side. Doesn't mean they're equal yet, because it's not necessarily true. We need to prove that, but we have proved that the left-hand side is a subset of the right-hand side. Now we're going to do it the other way around. Okay, guys, now for case 2, where we're going to prove the subset stuff the other way around. So again, we're going to do the element chasing idea. So we're going to say that X is some element inside of what I've now put on the left-hand side. It was on the right-hand side earlier. The union of the intersection of the A and the BI's. Okay, if X is in here, if X is in the union of the A's intersecting with the BI's, then there must be some set BJ, again, where X is in the intersection of A and that set, because it's in the union of all of them. So it has to be in at least one of them, right? So I can say again that there exists some J in the set I, such that X is in the intersection of A and BJ, okay? Hopefully that makes sense. And again, if X is in the intersection of two sets, that implies that it's in both of the sets. So that means that X is in A and X is in BJ. And what does that mean? Well, it means that it's in the intersection of A and the union of all of those sets. Okay, let me write that down. That tells us that X is in the intersection of A and the union of all of the BI's. Okay, and it's simply because it's in the intersection of A and one of the BJ's, so it has to also be in the intersection of the A and basically all of the BI's, right? Because it's in both A and BJ at the same time. So that means that it's also in both A, it has to be in both A and all of the BI's at the same time. So what this shows, and again, hopefully you can see this is literally just the right-hand side. What it shows is that this is a subset of this. What we showed earlier was that this one was a subset of this one, and because of that, they are both the same set. Okay, so final conclusion, the intersection of A and the union of all of those BI's is just equal to the union of the intersections of A and the BI's, like this. And this is our result. So these two things are the same as each other. That's our final result down here. Just going back up, don't worry, it's still going to be on the screen because I wrote it at the very beginning. But what we've now shown is the first statement is true. We've just proved the first statement. Again, you can probably now see the way that you're going to go about proving statement 2. So I would strongly suggest checking out, see if you can do statement 2. I'm not going to do it because, again, it makes the video really long. But once you've seen the method, this idea of element chasing, to prove that two sets are equal, element chasing is normally a pretty good idea. Just say that X, some element X is in one of them, and then show that that forces it to be in the other one, and then do it the other way around. Because just because an element is in one set, it implies that it's in another, doesn't mean they're the same set, right? For example, if I can prove that if a natural number is in the real numbers, then the natural numbers are the same thing as the real numbers. That's obviously not true, right? Just because a natural number is in the set of real numbers, it doesn't mean that the real numbers are in the set of all of the natural numbers. So you have to be able to prove it both ways. But other than that, that's it. So we've done all of that. We've done part 1, and see if you can have a go at part 2. If you enjoyed the video, if you found it useful, then I appreciate that. Like, share with your friends and family. Leave a comment, ask if you've got any questions, and I'll see you in the next one. Cheers.